There's a lot going on in today's video, so stay tuned. Today we're going to talk about when two representations of the same group are actually equivalent representations. And remember, in this series we're always working with a finite group, and we're representing it by complex matrices that obey the same relations that the group elements do. For instance, we're going to talk about this group D8, which has 8 elements, and I'm going to write down matrices encoding the generators. Here's a blue representation, and here's a red representation. Notice that they're different because these bottom matrices are not the same. We're going to show that these are in fact equivalent because in some coordinate system, they're actually the same. In fact, that's our idea behind the definition I'm about to show, is that in representation theory, choosing a different basis shouldn't affect anything, and we want to consider those things to be equivalent. So if you have one group, it's the same group, but two different ways of representing it using matrices, say blue matrices and red matrices, if there's a way to change coordinates so that all of the red matrices become all of the blue matrices, then we're going to say those representations are isomorphic. These blue matrices here are encoding a rotation counterclockwise and a reflection across the x-axis, whereas the red matrices are doing that same rotation, but they're doing a reflection across the y-axis. Those are different operations, but we're going to see if we just change our basis, they're actually going to be the same. Indeed, if I think of this as my new first basis vector and this is my new second basis vector, then if I write down these matrices with respect to that basis, now everything matches up 100%, and I can see that the blue representation is isomorphic to the red representation. You might want to pause the video and think about different things I could do. I could also have changed the way the rotation goes, or maybe even had it reflect across a diagonal line. It's a fun exercise to work out what happens in those cases. In addition to telling if two representations are equivalent, we also want to tell if a representation breaks down into pieces. Earlier in the series, we talked about what it would mean for a subspace to be invariant by a matrix. If such a subspace is invariant under all of the matrices in our representation, we're going to call it an invariant subspace. Now, the whole vector space and also the zero set, those are always going to be invariant of the group, but those are very trivial examples. And so our definition here is going to have the word non-trivial in there. And so if there aren't any ways of finding G-invariant subspaces other than the trivial ones, we say our representation is irreducible. For instance, if we have a two-dimensional representation, the only proper subspaces we need to consider about would be spanned by just one vector. Now, if we have an invariant subspace that's one-dimensional, that would mean the vector that spans that line has to be an eigenvector for every single matrix simultaneously. If we go back to our example, we can see that the eigenvectors of the pink operation are going to be the two coordinate axes. One has eigenvalue 1, one has eigenvalue -1, because this line stays fixed, but the other axis is going to get flipped. And you can check that neither of those eigenvectors is simultaneously an eigenvector for rotation. Rotation actually only has complex eigenvectors. So that shows that this representation is irreducible. And finally, for kind of an interesting example, let's think about this dihedral group acting on a 4-dimensional space, and rather than writing the vectors with like one column, I'm just going to write A, B, C, D as the sides of a square. And I want you to think of the rotation matrix as just rotating that square, and S as just flipping the square top to bottom. As a warm-up, can you find any eigenvectors that are simultaneously eigenvectors for both of these operations? If you pause the video and checked, you might have noticed a vector of all ones. Well, if we rotate or flip, it stays the same, so that's going to have eigenvalue 1. But this vector here of 1, -1, 1, -1, whether we rotate or flip, it actually goes to the negative of itself. So this is a vector with eigenvalue 1, this is a vector with eigenvalue -1, and this over here, this span of these two vectors is actually a two-dimensional invariant subspace. For instance, if you rotated the first vector, you would get the second vector, and if you rotate the second vector, you get the negative of the first vector. So under rotation, U and V form a closed system. Meanwhile, if you reflect the first vector, you get the same thing, but if you reflect the second vector, you get the negative of it. So in other words, U and V is a closed system with respect to R and S. And so if I give names to like the blue vector, the green vector, and these two red vectors, I can actually break this big 4-dimensional representation down into 3 smaller ones. 2 one-dimensional representations, their matrices would just be that eigenvalue. And then the two-dimensional representation we found in red is exactly the same as the one we talked about earlier in the video. This is called the irreducible decomposition of the starting representation. Notice we started with something of dimension 4 and it had 3 pieces, all of smaller dimension. I think we're really starting to have fun now. Thanks for watching.